Welcome to this explainer. Today, we're diving into something that literally changed the world. We're going to break down exactly what happened, the complex physics and cascade of human errors that caused it, and where things stand 40 years later. We're talking, of course, about the worst nuclear accident in history, Chernobyl.
Here is our roadmap for the day. First, the fateful night. Second, anatomy of the RBMK. Third, the fatal test. Fourth, containment and fallout. And finally, 4 decades later. Let's jump right in.
Section 1. The fateful night. A routine test goes horribly wrong.
Let's trace those critical hours. On April 25th at 1 a.m., operators started a planned power reduction at reactor number 4, just prepping for a standard safety test. But, things got delayed by the power grid, and over the next 24 hours, this highly sensitive test got handed off to a completely unprepared, much less experienced night shift. By 12:28 a.m. the next morning, power plummets out of nowhere. The operators are struggling to stabilize it, but they decide to push forward and officially start the test at 1:23 a.m. anyway. Just 54 seconds later, the reactor explodes. It was literally the perfect storm.
And when I say explode, I don't mean a small pop. The sheer force of this blast instantly blew the massive 1,000-ton cover plate right off the top of the reactor. It shot a massive fireball high into the night sky, completely obliterating the building and immediately releasing immense amounts of radiation directly into the atmosphere. But you really gotta wonder, how does a giant concrete and metal machine just blow up like that?
Section 2. Anatomy of the RBMK. Let's take a look inside the Soviet reactor.
Okay, to understand the explosion, we need to look at how this machine actually works. The core concept of the RBMK 1000 is pretty straightforward. Water pumps through the bottom, cooling the intensely hot uranium fuel. As it heats up, that water turns into steam, which is then fed to turbines to generate electricity. To control the nuclear reaction, to keep it from getting out of hand, operators use control rods that drop into the core to absorb neutrons. Basically, think of the water and steam as your gas pedal and the control rods as your brakes.
But here is an absolute game changer of a flaw in this design. It's called the positive void coefficient. In most Western reactors, if you lose cooling water, the nuclear reaction naturally just slows down and stops. The RBMK, though, it worked in reverse. As the cooling water boils away and forms steam bubbles, or voids, the nuclear reaction actually speeds up. The liquid water usually absorbs some neutrons, so when it turns to steam, there are suddenly way more free neutrons bouncing around, and reactivity shoots up.
Now, we also need to introduce a silent killer into this mix: xenon poisoning. Remember that 24-hour delayed power reduction we just talked about? Well, during that delay, a radioactive byproduct called xenon-135 was secretly building up inside the reactor core. Xenon strongly absorbs neutrons. It acts like a poison, forcefully choking the reactor's power down. Because the reactor was sitting at low power for so long, this xenon built up and unexpectedly crushed the reactor's reactivity down to barely 1% of its capacity.
Put all of this together, and you get an absolutely deadly feedback loop. Step 1. The water boils away into steam. Step 2. Because of that positive void coefficient, voids form, which reduces neutron absorption. Step 3. Those surging free neutrons then quickly burn away the xenon poison that was holding the power back in the first place. Step 4. With the xenon totally gone and the water turning to steam, reactivity just skyrockets uncontrollably. The reactor suddenly has all gas and literally zero brakes.
Section 3. The fatal test, where human error meets fatal design.
So, picture this. The operators are absolutely desperate to complete this safety test, even though the reactor has plummeted into a deep xenon pit. In their desperation, they flagrantly violate safety rules. Because power had dropped to 1%, they try to force it back up by pulling almost all the control rods completely out of the core. Not only that, they deliberately turned off the emergency shutdown computers. The reactor stalled out at barely 7% power, but they decided to start the test anyway. They slowed down the water pumps, which caused the little water left inside to rapidly flash boil into steam.
And this is exactly where the panic sets in. The water boils off, the xenon burns away, and power starts violently surging. An operator slams the AZ5 emergency scram button. This button is supposed to instantly drop all the control rods back in and stop the reaction cold. But, fatally, these boron control rods had graphite displacer tips. Graphite actually accelerates nuclear reactions. So before the boron stopping power could even engage, those graphite tips entered the core and briefly supercharged an already wildly surging reactor.
Because the reactor was already so incredibly unstable, we're talking no cooling water and nearly all control rods removed, sliding those graphite tips in caused a localized power spike estimated at over 100,000% of its design capacity. Over 100,000%. The intense heat shattered the fuel channels, jamming the rods halfway down. The remaining cooling water instantly flash-boiled, leading to the massive steam explosion that blew the roof completely off. Valery Legasov, the chief scientific investigator of the disaster, later recorded a truly profound thought on this. He said, "The accident was the inevitable apotheosis of the economic system which had been developed in the USSR over many decades. It is impossible to find a single culprit." He was pointing out that the disaster wasn't just simple operator error. It was the tragic result of a closed culture that prioritized cheap reactors over safe designs and kept critical safety flaws like those graphite tips a total secret, even from the operators running the machines.
Section 4. Containment and Fallout. The brutal immediate aftermath.
With the core completely exposed to the open air, a desperate battle to suffocate the intense radiation kicked off. Helicopters ran relentless, non-stop missions, dropping 5,000 tons of sand, clay, lead, and boron straight down into the burning reactor. And remember, many of the pilots and first responders doing this had little to no protective gear whatsoever.
The sheer scale of the cleanup that followed is honestly staggering. It involved up to 800,000 workers. These folks were known as the liquidators. These brave men and women exposed themselves to varying, often massive radiation doses just to clear the radioactive debris and construct the initial concrete and metal sarcophagus to seal up the ruined reactor. Dozens of early responders and plant workers tragically died of acute radiation syndrome within just a matter of weeks.
The explosion released at least 5% of the massive radioactive core straight into the atmosphere. This invisible threat drifted through the air, depositing onto crops, sinking into the soil, and completely infiltrating water bodies and agricultural pathways. The contamination forced the permanent evacuation of over 115,000 people from the immediate exclusion zone and severely affected massive swaths of Europe.
The political fallout was just as immense. Facing the international community in Vienna, investigator Valery Legasov detailed the operator errors, mainly to reassure the world that the Soviets had a handle on the situation. But privately, he later admitted, "I did not lie in Vienna, but I did not tell the full truth." Systemic design flaws and institutional secrecy were heavily censored from his report by the government. Tragically, the heavy weight of that cover-up, combined with his own severe radiation sickness, led Legasov to take his own life 2 years later.
Section 5. 4 decades later, the lasting legacy. So, where are things today? Well, the ruins are safely sealed beneath the gigantic 31,000-ton new safe confinement steel arch, which was carefully slid right over the decaying original sarcophagus back in 2016. In Belarus, multi-billion-dollar programs are slowly revitalizing agriculture and housing in zones that were once completely contaminated. And crucially, global safety got a complete overhaul. The World Association of Nuclear Operators was formed, and all remaining Soviet RBMK reactors were fundamentally modified with higher fuel enrichment and much faster shutdown protocols. A repeat of this specific reactor failure is now virtually impossible.
As you can see, the geographical impact spanned heavily right across the borders of Ukraine and Belarus. Now, nature has surprisingly reclaimed much of the immediate exclusion zone, turning it into a bizarre wildlife refuge. But the socioeconomic rebuilding in those outer regions continues to this very day, as entire generations learn how to live with these lasting ecological scars. And the political impact? It simply cannot be overstated. Former Soviet leader Mikhail Gorbachev later wrote, "The Chernobyl disaster, even more than my launch of perestroika, was perhaps the real cause of the collapse of the Soviet Union. The disaster permanently shattered the illusion that the Soviet system was infallible. It fueled an intense demand for truth and transparency that the old, rigid system just couldn't survive." While the physical physics of the RBMK have been fixed and international cooperation is better than ever, this explainer leaves us with one massive, lingering question. Have we truly learned the lessons of Chernobyl? In our modern rush for rapid energy, artificial intelligence, and ever more complex technologies, have we permanently cured that human tendency to prioritize progress over safety? Thank you so much for joining us to learn about this today, and we'll catch you in the next one.